Welcome to the math record. Today I'll be covering concavity and inflection points. First off, what is concavity? Well, concavity explains like the bendness of a curve. So this is either concave up, so concave up, or concave down. So in our video where I explained max and mins, I I said that every curve could just be broken down into a series of basic or a bunch of collection of concave parabolas that go up and down. So there's only a concave up or a concave down. So how do we know if it's concave up or concave down? Well, we actually use the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. And the reason is because if we do the same logic of what we did with max and mins, this derivative before the minimum is negative, the derivative at the minimum is 0, the derivative after the minimum is positive. So if we graph this, so this is our original function, this is our derivative, uh, we have a negative with 0 and positive. And a derivative of a parabola is going to be a linear function. Now you take the derivative of that. Well, this linear function has a positive slope, so that means it's positive. So as you see, the second derivative, positive, means it's concave up. So concave up. Now let's do the same thing for concave down. Choose 3 points. So we have our point before, point at our maximum, and point after our maximum. So this is concave up. This is a positive slope because the slope is the derivative is positive. And then this derivative is 0 because it's at a maximum. And the derivative here is negative because the slope is negative. Now this is our original function. So this is our derivative. So our derivative, we have a positive, 0, and then to a negative. So that gives us that if we take the second derivative, this is at a negative slope. That means this has a negative second derivative. So as you see, second second derivative, negative second derivative, and it's concave down. So an easy way to remember, if it's concave down, so it's going down, it's negative. If it's concave up, it's positive. Okay, so it's that simple. Now, let's understand the idea of inflection points. Well, inflection points actually just do with concavity. It's pretty simple. If you change concavity, then you have an inflection point. So if you change from concave up to concave down, you have an inflection point. Or if you change from concave down to concave up, you have an inflection point. So as we just said a few seconds ago, concave up is positive and concave down is negative. So if your second derivative changes from positive to negative, we have a inflection point. Or if our second derivative changes from negative to positive, we have a inflection point. So when does it change from positive to negative? At that instant. Well, positive to negative in our graph, in our original graph. And these are our original graphs. So when it changes, it goes through 0. It goes through. Okay, that was a bad picture. It goes through 0. And that is the two requirements that we had to check for inflection points. So if we had to have a point to check for inflection, we had to make sure that our inflection at the second derivative is 0, and we had to make sure that it changes concavity. Concavity. So it has to go from positive to negative or negative to positive. Okay, so it's pretty simple. Let's try an example. So let's say f of x is equal to x cubed So taking the first derivative, so that's 3x squared. Taking the second derivative, 3 times 2 is 6, so that's 6x. So when is this negative? Well, that's when x is negative. So that would be from negative infinity to 0. So it doesn't include 0, so anything less than 0 would give us a negative derivative, second derivative. That means at this interval is concave down. Now, when is this positive? That will give us concave up. Well, that's positive when it's greater than 0. So from 0 to infinity, positive, concave up. Now, when does it have an inflection point? Well, it changes concavity. Well, looking from here, from negative infinity to 0 to infinity, you change from concave down to concave up. So it changes right at 0. So that means we need to check if 0 at x equals 0 is an inflection point. So our two requirements is that the second derivative has to equal 0 at x equals 0 when we plug in x equals 0, and we have to make sure it changes concavity, which we already made sure because it changed it from concave down to concave up. So change, so to make sure the second derivative is 0, plug in 0 in here. 6 times 0 is 0. So this checks and this one checks. So that means at x equals 0, we have an inflection point. Inflection point. And that makes sense because let's just draw the graph of our parabola. Of our cubic. So it looks something like this. That looks a little bad. Okay, so something like that. So let's do both sections. So we have this section, and we have this section. So this section obviously is concave down. So we have negative. And obviously this section is concave up because it's going up. So concave up. And that's positive because it's going up, and concave down going down. Now we have our inflection point right here at x equals 0. And that's an easy way to remember it. So this is usually how I remember inflection points in concavity. I just think about a cubic. So if it's concave down, it's going down. If it's concave up, it's going up for the second derivative. So when we're dealing concavity inflection points, we're dealing with the second derivative. Then our second derivative for an inflection point, we gotta make sure x equals 0. Make sure the second derivative is equal to 0. And we have to make sure that it changes concavity. So it changed from concave down to concave up, or it changes from concave up to concave down. And that's basically it. Well, thanks for watching, and I'll see you at the next video.